Okay, just a couple things before we start. So first thing, your test date. Remember that's coming up in a couple weeks. So we've got this week to finish the moments of inertia stuff. We'll cover that this week. Next week here, we'll be doing the last bit for the semester on curves and surface area. Then that will be it for the applications for the semester. Then over here, the following week, we've got that revision. Yesterday, I sent out an email with a Google form link. Did everyone get that? Okay, so just check your emails. There's a link there that has the list of all the topics we've covered, right from U substitution all the way down. Please select the things that you want covered in the revision sessions. Okay, so during this week here, before the class test 2 and the June test, we'll have the revision. We'll just go by majority voting. So if most of the class selects U substitution, we'll do that first, and then we'll move down the list. Now, we don't have a lot of time for revision. We've got that tutorial period. I'll put a little revision test up for you to do. It won't be for marks. You can just try it out. Then we've got the Wednesday double and the Thursday single, and then that's it. Semester's over, right? Because then we have the test, then you've got your study break, and then the June test, right? So we don't have a lot of time. So please select the most important things you want to go through. Okay. Out of that list. So it's got everything from U substitution all the way to the last bit we're doing next week. Just select what you want, and then I'll put up the results and we'll go through that. Any questions on that? All good. Okay, so here we've got the test date, the 18th. There was a slight typo on the loan page. It said the 8th. Okay, but I told you guys last week it's the 18th. So 18th here is for the test. Then you've got a 2-week study break. Remember, from the 25th, we stop for the exams. Okay, you got your chem exams and your MATH162 exams, all of that stuff. So you got your study break from there. And then on the 8th of June, we have our June test / June exam. Did you see if there's any clashes with any of your other exams? So we're still good for 8th of June. No issues with that. Okay, 8th of June, we'll keep it at that. If something does come up, please just class rep, let me know. We can move it around a bit. But it seems like everyone's happy with 8th of June. Okay, and then after that, you got your long break, and then I'll only see you again in July. Okay, so after that revision period, we don't have any more maths until we get back after that long break. Right, any questions on that? All good. Okay, so again, just check that email. It has all of the important dates that you need to know. Right, so today we're going to start a new chapter on some applications to engineering. So we'll cover briefly these 3 topics here. You'll see this more in detail next semester in MATH162. Okay, especially that last bit there, moments of inertia, mass moments of inertia. We'll cover a few examples, but not too much. In the MATH162, it's quite a larger topic. Okay. Because remember, the MATH161 covers a lot of math stuff. The MATH142 is specifically applied maths. Okay, so it's like specifically this kind of stuff. Okay, so we're going to be calculating these 3 things. So the total mass, the center of mass, and the moment of inertia. If you are looking online for extra notes or YouTube videos and stuff, you might also see that last topic as mass moments of inertia. Those are exactly the same thing. It's just different naming. Okay. So if you're looking online and you see moments of inertia and mass moments of inertia, those are exactly the same thing, same calculations, same problems. Okay. So we're going to start off very generally going over what a moment is. So in math, we have this thing called the moments of a function. We'll see that these 3 over here are the 0th moment of a function, the first moment of a function, and the second moment of a function. You can get more. moments after that, but for our applications, we're only going to look at 0, 1, and 2. Much later on in your third year, when you do statistics, you will look at moments of a distribution. It's the same idea. Okay. So we'll look at it generally, and then we'll look at these 3 specific cases. Okay, so generally, what is a moment? Okay, so let's say we have some function f defined on an interval ab. The moments of the function are given by this. There's different notations, but we'll use this one. You might also see this written as xn with a little line at the top. It kind of means the average. Okay, so you have the square bracket notation for average, or you put a line at the top for average. Just note that does not mean vector. Okay, I know in your MATH162 and so on, you have vectors with the line at the top. This is not a vector, that means average. Okay, so this is given by the integral from a to b, x to the n, f of x dx. Sometimes this is normalized. We divide this by the integral from a to b, f of x dx. Okay. So usually in general, we write it like this with that normalization at the bottom. Otherwise, we leave that out if the function is already normalized. Okay, so this is what we have. This n over here in the exponent, that tells us which type of moment this is. So if n is 0, then it is the 0th moment of the function. That's just the total area of the function. So integral from a to b, f of x dx, that's the area. That's the 0th moment. If n is 1, that's the first moment. If n is 2, that's the second moment. Okay, that's the idea. So n is 0, this is the 0th moment. N is 1, this is the first moment. N is 2, it's the second. And again, you can continue this 3, 4, 5, but for our applications, we're only going to look at 0, 1, and 2. Okay, and then this is the second moment. Okay, and we'll see that for our applications, the 0th moment, that corresponds to the total mass of whatever object we're looking at. The first moment is the center of mass. And the second moment, that is the moment of inertia. So that links these 3 together. Now, from now on, we're not going to be talking about those moments. That's just to give you an idea of where these things come from. From now on, we're only going to look at the application side, right? The engineering side of total mass, center of mass, moment of inertia. Okay, so let's have a look at the first one, the total mass. Pretty straightforward to work out. Okay, so number 1, the total mass. Okay, so how do we work out the total mass of something? Usually we are given the shape of this object that we're dealing with. Let's say it looks something like this. Okay, some weird shape, right? We want to work out the mass of this thing. If this was a nice shape, like a cone or cylinder or pyramid, right, we know how to deal with those shapes. If we're given some funny shape like this, we need to do something different. So what we're going to do is take this funny object, whatever it is, and cut it up into little pieces that we can work with. Okay, so this is some weird shaped thing. We're going to cut it up into little cubes. Little cubes like that, where each of these little cubes has some tiny mass we're going to call dm. Right, it's the limit of delta m, right, change in mass. Okay, so dm, that's a tiny bit of mass in our object. Okay, so if we know the mass of a little piece of the object, how do we find the mass of the whole object? Right, we need to add it up. Okay, we're going to add up all of the pieces. Now, if these were individual points, we could just sum them up. Okay, if it was like individual blocks, we could just add it all up. But here it's an infinitesimal amount, dm. So instead of adding all of the pieces together, we have to integrate them. So here we're going to have capital M. We're going to have that as our total mass is going to be the integral of dm. It's the integral of our little mass pieces. Okay. Now, this is the definition for the total mass of some weird object. But to actually calculate it, we're going to have to rewrite this in a form we can work with. And this dm, we're going to rewrite using the density of this object and the volume of this object, because then we can do the integral. So recall what the density means. The density rho, you should be familiar with this from physics. The mass density of an object, that's going to be the mass divided by the volume. Right, mass density, mass over volume. I'm sure you've seen that before. So what we have there is for something that has a constant density. If I give you some object, if the mass is constant throughout, then the density is constant throughout, right? Now, what happens if the density is not constant throughout? It's going to change from point to point. In that case, it's not going to be a constant density. It's going to be some rho is dm by dv. So here we have rho of x, y, and z. It changes from point to point around the volume. So instead of just the quotient m over v, we need to write it as a derivative dm over dv. So this first one, this is constant density. Okay, constant mass over constant volume. But at the bottom there, that is a non-constant density or inhomogeneous density. Have you worked with the inhomogeneous densities in physics? No. Okay, that's fine. We'll go through it. Okay, so here this is an inhomogeneous density. It changes as we move around the shape. We're going to rewrite that a little bit. So that dv, we're going to take over to the other side. So we're going to get dm is rho dv. So we take our density rho, that's the mass per volume. We multiply it by volume. So mass per volume times volume, we get back to mass. So that is the mass of that little piece located at some xyz. Again, that rho is a function, rho xyz over there. Okay, so in this case, we have something like this, where at some point here, xyz, okay, at some point, again, all the points are different. The density is different all over. There's going to be a little cube. So at that point, xyz, that little space there has a density rho xyz. That little cube has a volume, right, dv. So the mass of that little cube there, dm, is going to be rho xyz. You know, at that point, xyz, it's got some density rho times the volume of that little cube. Right, it's just a little cube. We can work out the volume, dv. And again, we can do the same thing we did before here. So we got a little piece. The total mass is the integral dm. Now we know dm, it's just the density times the volume. So the total mass m is just the integral of rho dv. Okay. So please put a little box around that. This is the total mass of the object given some density rho. Okay. Now, when we're actually calculating these things, this dv will depend on what shape we're given. So if we're given some shape like this, so let's just say here, example 1. Okay, so something very simple to work with. So we've got a cylinder like this, okay, very easy to work with. And I'm going to say that the density changes as we move up the cylinder. So rho of XYZ okay, rho of XYZ. So we got XY, we got Z going up. This is going to be given by, let's say, 2Z squared. Yeah. So again, we've got our little coordinate system like this. Okay. And the density of the cylinder is not uniform. It changes everywhere. But as we move up the cylinder, the density increases. So at the bottom, it's got very low density, very small z, very low density. As you move up the cylinder, it's going to have a very high density. Right? It increases with z. Okay, so that's the density. What we want is the total mass of the cylinder. Okay, what's the mass of this thing? So we're going to use our formula over here. So the total mass is the integral of the density dV. And again, dV depends on what shape we have. So this is a cylinder. When we were calculating the volume of these things, what did we use for a cylinder? What method? There's 4 methods that we can pick from. If we have a solid cylinder, we're trying to work out the volume. What did we use? Starts with the D. Disc method. Yeah, we can take the cylinder and we can cut it up into discs. So here, let's cut this up here. Okay, so we're cutting a little disc out of our cylinder and we can work out the volume of this thing. So dV. That was the cross-sectional area. So it had the area pi r squared. And if we wanted the volume of this thing, we would have dV pi r squared dz, right? Because we're stacking them along z. We'd write it like that. Okay. Is that okay? Everyone good? Okay. So what do we want to do here? We want to work out the rho. How do we do that? We use the formula here, integral rho dV. Again, so we figure out what's dV. We see that we can slice this up into discs. So dV we can write like that. So now what does this integral become? So instead of integrating over the volume, we now integrate over z. You see that? dV is pi r squared dz. We just integrate over z. Much easier to do. Okay, so let's set this up. Okay, so we got our cylinder. So let's say the radius is capital R. It has to have some radius there. Let's say that the height is h. Okay, so we set up our coordinate system so we can put down some values. So our total mass m is going to be the integral, little rho there, dV. So this will be the integral rho. dV is the little volume of a disk that we cut out. That was pi r squared dz. So pi r squared, we know the radius of this thing. dz. So all of this here, this was EV. Everyone clear on that? So let's substitute rho. We know it's 2z. So this is from 0 to h. So pi, we can take out r squared. That's a constant we can take out. Integral from 0 to h. We're left with 2z. 2 we can also take out there. Okay, so we're left with this. Straightforward integral in terms of z. So let's work this out. So this will be 2 pi r squared. This will be 1/3 z cubed from 0 to h. So this will be 2 pi r squared. Okay, we can substitute h there. We're going to get 1/3 h cubed. If we put in 0, we get 0. So this will just be 1/3 h cubed. So here we have 2/3 pi r squared h cubed. All right. Is everyone okay with this example? The 2 from the density was 2z squared. Yeah, 2 is a constant. We just took it out to the front. All right. Any questions for this first problem? Yeah? You have a question? Oh, you good. Okay. Any questions before we move on? All good. Okay. Let's have a look at another example. Okay. Example 2. We're going to have, let's say, a cone. Okay, so for now, we'll look at, the simple solid shapes. Later on, we'll look at some more complicated volumes. Yeah, but just for now, we'll keep it simple. Okay, so we have ourselves a cone. This is going to be a non-homogeneous cone, right? The density is going to change as we go around the cone. And it's going to be given by the following. Yeah, we'll keep it simple. 3x. Yeah. 3x squared. Sorry. Okay, 3x squared. Okay, so if we are at the center of the cone, going through the middle, the density is very low. But as you move along x to the one end of the cone and the other end, the density is going to increase. Okay, that's how you should picture this. So what we want to do is work out the volume, the mass of this cone, given that the density changes as we go around. So let's set up some coordinate system, can put in some values, and then set up the integral. Okay, so let's redraw this. Okay, so we're going to have something like that. Let's put in some values for this cone. Let's say that the base radius there is capital R. And let's say that the height of this cone here is h. What we want to do is work out the total mass. So let's put the equation down, then we can see what we can do. So this will be the integral dm. That's our starting point. But we know we can write this as the integral rho dv. So we have rho, that's going to be 3x squared. Yeah, so that's fine. This dv now, we need to choose depending on the shape, right? And then the choice of dv, right? We can use the disk method, where dv is a disk, washer method, where dv is a washer, the shell method, where dv is a shell, right? It depends on what this shape looks like. Yeah. So we know rho is 3x squared. Yeah. So given the shape, given rho, what should we use for dv? Cross-section method, disk method, washer method, shell method. What can we use? Okay, we're integrating, remember, something with x squared here. So it's not changing with height. The height is fixed, right? The density along z, that's fixed. It is changing along x. Okay, so keep that in mind. So if we're stacking vertically, you would do something like this, right? Because it changes with z. Here, it's changing with x. That's in the radial direction, right? So we've got this cone here. Again, z, the density is constant. Any z value, it's constant. Here's the hint. If you go radially outwards along x or y, the density is changing. So what should we use? What? Washer. No, it's solid. Solid cone. Okay, think about it. It's changing radially. That's your hint. Maybe I should give some points. Not quite. Cross section is like the disk method. We stacking vertical. The shell method, yeah. Why? Because the shell method was 2 pi RH, right? It was with respect to the radius. Yeah, we can use the shell method. Okay, so let's set this up to use the shell method, and then we can work it out. Okay, so I'm just going to do a slice, right? For the shell method, we need a slice of this thing. So it's going to look something like this. Okay, it's going to go around like that. And as we go along x here, as we go along the radius, okay, the density is going to change going along there. Okay, so what will dv be in this case? Like we had over here. This one here. So we cut it up. We got dv. So this one here, we're going to have to do something similar. No, not the area of the triangle, the shell, the volume of the shell. Okay, think about it. Right, we've got this. Sorry, not x squared, sorry. Sorry, it's supposed to be r squared, the radius. Remember I said it's radially out. So it's 3x squared plus y squared, sorry. This is supposed to be the radius. Yeah. So it's the radius of the shell, x squared plus y squared. Okay, so we got this r here. How do we set up the shell to have that radius? Yeah. No, not pi r squared. Remember the shell? It was the circumference times the height times the thickness. What was that? Someone said? Yeah, 2 pi RH. Good. So here we're going to set this up to be a shell. Right? At some radius, there's going to be a shell there. So this dv, 2 pi RH dr. Right? Did everyone see that? From the shell method we did last week? Okay. So here, 2 pi r, that's fine. We know what the radius is going to be. It'll be along x there. What about the height? We need the height of this shell here. What will that be? So it has a radius r, that line over there, right? The x-intercept will be the radius r. The y-intercept will be the height h. So what's the height of that little pink line over there? It will be z equals something. Right, we did this calculation before when we did the volume of the cone. We need the height of the shell at that point. So we need the z value along that line. So what's the equation for that line? Okay, what's the gradient of that line? H over r, close. It's a downward sloping line. Negative h over r, yeah. Right, it's got some height h, it's got some radius r, negative h over r. And then the rest of it, that's the gradient. So times x. What's the y-intercept? Yeah, h, it's the height. Yeah. So that gives us our height of the function. Okay, so we can put this all together for our dv. Okay, so let's write that out. So m, that's going to be the integral from 0 to r. Okay, going along the radius there. 2 pi r. Okay, from the shell method. 2 pi r h. Let's call that x there. So 2 pi x, that's for our radius, minus h over r x plus h, that's the height. And what about the density? Yeah, that's the radius squared, right? X squared plus y squared, that's the r squared. So what will that be over here? What's the radius? The shell, what's the shell radius? Yeah, the pink cylinder. What's the radius of that at that point at the bottom? We just wrote it here. The shell method. 2 pi. The radius. What's the radius? Come on, guys. We just wrote it. 2 pi x, 2 pi rh. What's the radius? X. Yeah, the radius is x. Come, please. Okay, so 2 pi rx. So here we need the radius squared. So what do we use? X squared plus y squared. That's this radius here, right? From the axis going outwards. That's the radius squared at that point. We drew this little diagram here. We've got the radius going along x, right? For the cone, that's the radius going outwards, and the height is going along z. Now we want the radius squared. What is that? In this diagram that we drew. Hey, you guys got a test on this in 2 weeks. Okay, think about it. Okay, we've got this 3D shape, right? With x, y, z. We got the 3D shape, right? So x, y, z, we said that the density was x squared plus y squared, which was the radius squared, right? For this thing. Now we took a slice. We cut it to make it easier for ourselves. We cut it into 2D. So we did a slice and we've got this. So z, that's the height. X, That's the horizontal part of our slice. That triangle, when we rotate it around, makes our cone. In the original picture, we need the radius squared, right? In the 3D picture. In our new picture here, we still need the radius squared. What's the radius? What's that? X squared, yeah. That's going to be the radius squared. So here we've got something like this. Okay, we've got our shell, right? That's going to be rotated around. This distance here, that's the radius we're looking for, the radius of the shell. But in our setup, we called that distance x. Right? This is x. This is z. So the radius squared is x squared, which is what we need for this picture here. Does everyone see that? Yeah. Everyone good? Sure hope so. Right, because we took a slice. We slice it. So we take a slice of this. We get this following picture here. Or you can complete the picture if you want. That's still the radius over there. Okay, so let's fill that in. So all of this in front here, that's our dV from the shell method. And this little extra bit here, that was the density. Okay, and then the 3, that's a constant. So we can just take that out of the integral. Okay, so let's work this out. So 2 pi, that's just a constant. We can take it out along with the 3 there. X squared and x, that will be a x cubed. We can put that here. Yeah, then we can distribute, and then the integration's pretty easy from there. Okay, so let's do the integral. Okay, from 0 to r, because we're going along x, that's the radial direction. So if we put in 0, we just get 0. So let's put in r. So r to the 5 over 5 plus h over 4, r to the 4. Okay, first term there, we've got r to the 5 at the top. We've got another r at the bottom. That can cancel. So we're left with minus a fifth, h over 5 r to the 4, plus h over 4 r to the 4. That's good. We can add these together. So a quarter minus a fifth. Hey, you guys are sleepy this morning. Okay, quarter minus a fifth. Keep in mind that next year you don't have your calculators with you. You know that, right? Okay. So let's try avoid the calculator usage for now. So a quarter minus a fifth. 1 over 20. Yeah. No, we got something like that. All right. Any questions for this one? Yeah. This in pink. This one. Yeah. So this first part, this is from the shell method. 2 pi x f of x. Remember, that was from the shell method. That was dV in the shell method. But what's the density? Remember, it's rho dV. What was the density? It was 3 times the radius squared. What is the radius that we use in the shell method? X. So it will be 3x squared. Yeah, please don't mix up your variables and stuff. So in the shell method, when you're integrating the radius, we integrate along x. That is the radius. So here, 2 pi r, the radius of the cylinder, is 2 pi x, because we integrate along x. Here, this x over here, that's the radius of the shell here, right? Minus h over r times x, again, the radius. The density was 3r squared, the radius squared. In the shell method, the radius is x. So wherever you have radius, you put x for the shell method. Yeah, so here, let's just write this out. So shell method. Replace radius with x. So you got the integral from a to b. 2 pi r is 2 pi x. The height of the function is f dx, right? We did that for the shell method. Okay. Any other questions for this one? All good. Okay. So example 3, that will be for homework. You can try this out. Okay. So we have the same sort of thing. We've got a cone. The rho equals 1 minus z. Okay, where we have a height of 1 and a radius of 2. Okay, so it's a fixed solid cone, height of 1, radius 2, so it's like a squash kind of cone. And the density changes as you go vertically. So at the bottom, it has a high density when z is small, has a high density at the bottom, low density at the top. We need to integrate vertically, right? Because the density is changing with z. So you have to integrate vertically, right? That's all the thinking you have to be doing. So which method? We want to integrate vertically along the cone. This method, exactly. Okay, because previously the density was changing with the radius. So we used the shell method because it was with the radius. Here the density is changing vertically. So we want to stack it up vertically. So we need the disk method. Okay, everyone clear on that? Okay. So again, this dv that you need to pick depends on the shape, right? When you draw the picture, it depends on the shape. It also depends on the density. Is the density changing vertically? Are we going to stack up using the disk method? Is the density changing radially? Are we going to use the shell method? Is there a hole in the middle? You know, you have to use the washer method, things like that. Okay, so that's your hints for this one, disk method. Okay, so we're going to be stacking these vertical disks. Okay, and then, so that's the stacking process for the disk method. Each of these is going to have a different radius, right, with Z. And each of them is going to have a different density with Z. Does everyone see that? Yeah. So as you go up from the bottom, each of them will have a different radius. You're going to have to figure that out. Each of them will have a different density. You'll have to figure that out as well. Okay. Any questions for the homework? Well, good. Okay. So that's calculating the total mass. Again, very similar to what we did with the total volume. Okay, same idea. For the next one, we're going to be calculating the center of mass. Okay. So we'll start very simply with a bunch of points. Are you familiar with center of mass from physics? No? Yes? No? Okay. So we'll start off with a very simple picture, and then we'll go into the continuum case. So let's say we have our origin O, and our axes x, y, z, and we have a bunch of points. Let's say we got 4 of them over here. Okay, 4 points. Each of them have a different mass. So M1, M2, M3, M4. And they're moving around whatever physics thing you covered. Okay, so what we want to do is find the center of mass of the system. So it is the mass weighted average, right? Okay, so it's the average of all the points, all the positions weighted by the mass. So if one of the masses is very heavy, the center of mass moves closer there because of the weighting. If the other masses are light, it's kind of further away from those. So each of these has some position vector, R1, R2, R3, and R4. Okay, so that's just the positions relative to some origin you pick. That doesn't really matter. So the center of mass, COM, center of mass, also given by capital R, usually in physics. This is going to be given by the mass-weighted average of the positions. So again, if one of the particles has a very large mass, that's weighted more. Okay, it goes closer to that one. So this is going to be M1 R1 plus M2 R2 plus M3 R3 plus M4 R4. All over the total mass. Right? Because when you average, you divide by the total. Okay. Everyone okay with that one? Okay. You should be familiar with that formula. Now, what we're going to do is split this up into 3 separate equations. Because remember, this is a vector equation. The vector equation has 3 components. There's the x component, y component, z component. Okay, so we're going to split it up into 3. So the first component, x, that will be the x components from each of those. So that's going to be the sum mi xi over m1 plus m2 plus m3 plus m4. That's just the total mass. Let's call that capital M. Yeah, so we have something like that. Then we can do the same thing for the other components. We can find the center of mass for y. We don't need the vector anymore there. So we can write this as the sum mi yi over the total mass. And the center of mass component for z, this will be the sum mi zi over m. Yeah. So we just split up our vector equation into these 3 here. Okay. Everyone okay with that step? Okay. Okay, so what we're going to do now is move away from these points over here and look at the center of mass for a solid object. Okay, so not a bunch of points that we can add, but some solid objects. So let's draw some picture. Again, we've got our coordinate system. Some origin O. And now it's not a collection of individual points. It's now a total solid object. So again, we're going to pick some points here. There's going to be a little mass piece, like we had at the beginning when we worked out the total mass. At that point, there's going to be some density rho. I'm not going to repeat all of that. We covered that. So that's rho x, y, z. and there's going to be some vector going to that point, right? Okay, some vector going there. Okay, so we want to do the same thing as we did before with this picture. We had a bunch of individual masses, we did the weighted sum, and we've got our center of mass components. We're going to do the same thing here, but instead of adding up the points, we now have to integrate up the little mass volumes. Okay, so instead of a sum, it's going to be an integral. So it's going to be the integral. Instead of xim, it will be x dm, the little mass piece. And then at the bottom, instead of the sum, m1, m2, m3, m4, it's the integral of the little mass pieces. Everyone see how we went from the sum to the integral? Very clear. Now this bottom part here, integral dm, that's just the total mass m. Very easy. Okay, so we have that for the center of mass Rx, and we can do the same thing for Ry, Rz. So we have these three. So if you want to find the center of mass of some object, you calculate these three, and that will give you the center point. For example, if you do this for a sphere, okay, you find Rx, Ry, Rz, it will just be the center, right? It will just be the origin. If you have something a little bit more complicated, then the center of mass will move around. Okay, so let's have a look at example 1. Okay. So we'll look at one example in 3D, one example in 2D, and then I'll give you a homework problem. Okay, so example 1. Let's do something very simple. Back to the simple cylinder. Okay, so it's a cylinder with radius r, height h. We want to find the center of mass. And now for this simple example, we're going to say that this is a uniform solid. So the density is constant throughout. Okay, just to make it a little bit easier. So this is a uniform solid. So it has a constant density. Okay, so rho xyz is just some number rho. Okay, solid, a uniform solid. Okay, now before we get to all of the calculations, let's have a little guess as to where the center of mass will be. It's good to have a guess first. Then we'll do the calculations and see if it makes sense. So the center of mass will be some xyz. So let's set up some axes so we can work with numbers. Okay, so x and y, those are radial. It's going out radially. Z, that's going up and down with the height. So what do you think the values of x and y should be for the center of mass? Just like a gut feeling, right? You've got a uniform solid. Where do you think the center of mass should be for x and y? 0. Yeah, 0, 0. Should be right in the middle. What about z? H over 2. That seems reasonable. So we have a guess for the center of mass. It's a very reasonable guess. Okay, 0, 0, h over 2. Seems pretty reasonable. Let's do the long and boring calculation. We should end up with this. Okay. Well, ask him. It's in the middle. Yeah, halfway point. Exactly. Yeah. No, it's always good to think about why you're guessing these numbers. Okay, yeah. So it's the halfway point. So in terms of the radial direction, you go this way for r, you go this way for minus r, halfway 0. You go up and down, halfway point is h/2. It's the middle. Okay, everyone clear on that? Why it should be the middle? Okay. Okay. So let's work it out. This h/2 part I'm going to do with you, and then these x and y you're going to do for homework. Because it's symmetric, you only need to do one of them. Okay. So if you do it for x, y is obviously the same, but z, that will be different. Okay. So homework, you do that one. I'll do the z one in class. Okay. So what do we want? We want rz. So that's going to be 1 over m integral z dm. That's the general formula. Given a solid, given the density, you then need to substitute accordingly. Okay, firstly, the total mass. It's a uniform solid with uniform density rho. We can work out the volume. So what will the mass be? Remember, density is mass over volume. We know the volume. We know the density. What will the mass be? Volume times density, exactly. What's the volume of the shape? Cylinder? You have to know these simple ones. In the test, you're going to get some funny shape. You need to know these basic ones first. What is it? Pi r squared h. Okay, so we got our mass m. So we can substitute that at the end there. Okay, next we need the integral z dm. Dm we're going to replace with rho dv as we did before. So r of z is 1 over rho pi r squared h integral rho dv. We are integrating vertically because of z. We want to integrate vertically. So we need the disk method. We're going to stack up our disks vertically. So this will be the integral with the disk method from the bottom of our shape, z is 0, to the top of our shape, z is h. So you need to be very clear with the disk method so you can apply it. Okay, we've got z, so we can leave that there. dm, that will be rho dv. We know it has constant density rho, so we can put that in. And dv for the disk method. Disk method, stacking up vertically. What is it? Yeah, we just did it like a couple minutes ago with where is it? This one. Pi r squared dz, right? Okay, please make sure you go through this. Your class test 2 is mostly this, right? Volumes and inertia and center of mass. Okay, the disk method goes throughout. Finding volumes, finding mass, finding center of mass, finding inertia. All of it is these volume type questions. Pi r squared dz. Okay, so let's put that in. Everyone clear with that? Okay. Rho pi r squared, all of that is constant. We can take it out. That's what we have at the bottom there. Right? Rho pi r squared. We can cancel that. Okay, everyone see that? Took out the constants, cancelled, got that. This pretty easy to do. Okay, if we substitute h, we get h squared. 0 just gives us 0. So this is going to be 1/2 h squared over h. Hey, that looks great. We have our answer, half h. All right. Everyone clear on that? Okay. So we got our half h for the z component, which is what we wanted. For the x and the y component, you're going to do that for homework. So I'll set it up for you, and then you can do the rest. So again, because it's radially symmetric, you can pick one. The other will give you the same answer. So let's say we go along y. So the radius, not y, we're going along outwards. What are you going to use? We're slicing it along y. Not the shell. Cross section. Yeah, we're doing the slicing along y. So it's not the radial, because it's not in terms of the radius, but we're going along the x-axis or the y-axis. You pick one, and then you slicing it. Cross section. Okay, so pick one of these to do for homework. You should get 0, and then the other one will also be 0. Okay, by the symmetry. Okay, so homework. Show that our x equals our y equals 0. Okay, again, don't do it for both, just do it for one of them. The other will also be 0. Right, any questions for this example? All good. Okay, example 2. Okay, we'll do one more 3D case, and then the 2D one I'll leave for you to do. Okay, it's not too bad. Okay, so example 2, let's make it a little bit more difficult. Okay, so we've got a cone, again, pretty simple, but now the density is going to change. Okay, let's say it has a height of 2 and radius 1. Okay, so the density changes with z. As soon as you see that, you need to start thinking to yourself, how am I going to cut the shape up for the integration? Okay, so we've got a cone. We know we can slice it up nicely, right? This method, we can slice it up. The density depends on z. That gives us another clue. So what method should we use? Don't say shell. Okay, what do we use? Slicing it up vertically. This method, yeah, we're going to cut it up vertically. Okay, so let's work out what our little disk is going to be, and then we can do the integral. Okay, so we're going to have a disk. As we go up vertically, the radius is going to change. Right at the bottom, the radius will be, what will it be? 1 at the bottom. And then at the top, 0. The radius is going to change. So let's work out how the radius changes with z. Then we can just substitute for the disk method. Okay, so we can just do a little picture like this. So the total height is 2, the radius there is 1. We want to know how does the radius depend on z. Okay, so we got a little picture there. As you move up from 0 to 2, that radius is going to change from 1 to 0 as we move up. So what's that going to be? The radius, that's the x value that we've got there. We want the x in terms of z. Well, what can we do? Yeah, can get the equation of the line. Good. So that will be z equals, what's the gradient of this line? 1. Oy, need to send some of you back to 160. Okay. Gradient of the line? -2. Good. Y value 2, x value 1, and it's downward sloping, -2. Y-intercept? 2. Okay, let's do a quick check. When we're at the bottom, what's the radius going to be? Z is 0 at the bottom. X will be 1. Yeah, that's what we wanted. And then at the top, when Z is 2, X will be 0, right? If Z is 2 at the top, X will be 0. Okay, so that works out nicely. So we need the radius, which is the X value. So we're going to have here 2X is equal to 2 minus Z. So X, that will be 2 minus Z over 2. That's the radius that we need for the disk method, right? As we go up. Okay, so let's write this out. Okay, so we want RZ. Okay, again, I'll do the Z1, the X and Y we can talk about afterwards. So RZ, we're going to use the disk method to stack vertically. So we need 1 over the total mass. We'll get that later. Integral from 0 to 2. Okay. Then we need Z dm, right? Okay, so we need Z dm. But dm, we're going to replace with rho dv from before. Right, I'm doing it step by step, but obviously you'll substitute everything at once. Okay, so rho, that will be Z from what we got there. And dv for the disk method will be disk method, this one. What's the volume of this? R squared dz. So we've done all of our substitution. Everyone clear on the subbing part? You're right? Yeah. Okay. Any questions getting to this stage? Okay. Okay. What about this M in front? What's that going to be? What's the total mass of the shape? How do we work that out? Check back in your notes for the total mass parts. So we've substituted everything. We need the total mass for that denominator. What do we do? There's a little hint from what we just wrote there. Not just times volume. Is this a uniform shape? No, it's not. The density is changing. So to find the total mass, it's not just density times volume from what we did before. we have to do that integral. Everyone clear on that? Okay, it's non-uniform. So to get that total mass, we have to do the integral m is equal to the integral from 0 to 2 rho dv. Everyone clear on that? Okay, so let's do this quickly on the side, and then we can substitute. So here we need to do a sub-problem to solve the first problem. In the test and exams, the way I'll phrase it is I'll give you some solid. Part 1 will be finding the mass. So you already have that number. And then part 2 will then be finding the center of mass. Okay, using what you have from part 1. Okay, so I'll break it up into steps. Okay, but here we do this as a side calculation to find the total mass. Once we have the total mass, we can substitute and then find the center of mass. Okay, but in the test, it will be broken up into 2 parts. Maybe like 5 marks kind of thing. Okay, let's work this out. So the pi from the pi r squared, we can take that out. Then in the brackets there, we got 2 squared at the bottom. There'll be 4. We can take that out. So we have the integral from 0 to 2, z 2 minus z squared dz. So we have pi over 4, z 4 minus 4z plus z squared. So we get pi over 4, 4z minus 4z squared plus z cubed. Okay, integrating, very easy. So 4 over 2, so there'll be 2z squared minus 4 over 3 z cubed plus 1 over 4 z to the 4. If we put in 0, we just get 0, so we can just put in 2 there. Pretty easy. What do we get for that? Okay, so the first one, 2z squared, what do we get? 8. Next one. No calculators. Come, we need to work on no calculator usage. Okay, you get to your math 238 next year, you don't know what to do without your calculator. 32 over 3, yeah. Next one. 32. No, 2 to the 4? I'm hearing many different numbers. Over 8, sorry. Sorry, I was thinking z cubed is 8. 2 to the 4? Hey, I'm tired. Yeah. Last one, what do we get? 4. Okay. Okay. And then add this up. What do we get? Yeah, bottom factor 3. So 8 times 3, 4 times 3. Over 8. Okay, let's double check. Someone else, what do you get? 4 over 3. Okay, we've got a few 4 over 3s here. Anyone else? 4 over 3. Okay, let's go with that. Everyone agree? Okay, if it's wrong, that's your fault. Okay, pi over 3. Okay, so in the test and exams, this would be like part 1, get the total mass. And then part 2, you would then substitute and then do this next integral. Yeah. Sorry? 1 over m times m. This one. No, it's non-uniform. You have to do the integral. So in this, where is it? This one here, we could just multiply it because it was constant. But for this one, you have to do the integral. Yeah? This bit.
Yeah, that's E.
The row. Yeah. There's 1. No? No, it won't be 1. This over here, the center of mass is Z rho dV. This one is just rho dV. Remember, it's the x to the n for the moments. So for the 0th moment, that's this one. It's just rho dV. For the first moment, it's Z rho dV. And then for the next one, moments of inertia, it will be Z squared. Yeah, they're different. Yeah. Okay, so let's substitute that in. Quickly do this. And then we'll look at the moments of inertia tomorrow. Okay, so we've got m now. That's pi over 3. So we flip that around, integral 0 to 2. Okay, let's simplify this if we can. So we're going to have pi over 4 from here. We can take that out. Pi over 4. We're going to have z squared from this first part, and then 2 minus z all squared from the second part. Okay, again in the test and exams, this would then be your part 2, okay, after calculating the mass. Okay, so this will be 4 minus 4z plus z squared dz. I'm not going to do the full integration just because of time. You can do the rest from there. So we're going to have 3/4 integral from 0 to 2, 4z squared minus 4z cubed plus z to the 4. So we have 4 over 3 z cubed minus z to the 4 plus a fifth z to the 5. Okay, and then over here, you can do your substitution. Okay, I'm not going to go through all of that again. You can do all of that. Right. Any questions for this example? All clear. Okay. Then for homework, you're going to do a little proof on the side, and then you'll answer a little question. Okay, so homework. Okay, center of mass in 2D. Okay, it's a little bit simpler than the 3D case. So there's a little proof for you to do to get the equations, and then you'll use the equations for the calculation. Okay, so in 2D, we have the following equations. So the center of mass for x is given by 1 over m integral from a to b, x, f of x minus g of x dx. And for y, it will be 1 over m integral from a to b, 1/2 f of x squared minus g of x squared dx. Okay, so this is for a 2D region where we have some upper function f and some lower function g, and that gives us some bounded region. Okay, so upper function f, lower function g, that gives us this region here. Okay, the region has some density over that region there, okay, for f, and g. Okay, so what we want to do is show that we get this for Rx and Ry. Okay, now instead of using rho dV like we had before, this will now be rho dA. Okay, it will be the area of this. Okay. Okay, so we have rho dA. Show that we get these two equations here, very similar to what we did in the beginning. Okay, so we've got these masses in 3D rotating around, doing whatever. We get this, okay, for Rx, Ry, Rz, but now we're only focusing on the first two. Okay, so Rx and Ry. Okay, so for homework, try get this. And then work out the center of mass for the following shape. Okay. So it's this bounded region with y equals x and y equals x squared. Okay, there's going to be some center points. The center of mass there is all uniform density. Find the center of mass. Okay. I'll give you a little hint. This over here looks very similar to the washer method. Okay, looks quite similar to that. I'll leave that as your hint there. Washer method, disk method. Okay, think about that. Any questions for the homework? All good. Okay, so that will be it for today. Tomorrow we're going to go through the moments of inertia. If you're unfamiliar with that from physics, please read up on that for tomorrow. Okay, moments of inertia, mass moments of inertia. Okay, different names means the same thing. Right, any questions about today's work? All good.